Okay, so I'm from NUS, so thanks for the invitation to this workshop. Okay, so I want to talk about AI algorithms or AI problems. So one of the issues from the very start of AI is that almost all the interesting problems that we want to solve in AI, they're all computationally hard. Right? They're all intractable. So then we ask why, right? Humans seem to be able to do those type of problems fairly easily. So is it because we try to solve the worst case, right? All of these problems in the worst case is hard, but maybe the typical cases is not so hard, and right, maybe we should be trying to solve for typical or average case performance instead. Okay, and I want to argue that the machine learning provides excellent tools for doing that, because that's how we do machine learning, right? We get a set of training set. So in this case, it will be a set of problems that we want to solve. And then we learn. If we do well on the training set, then generalization theory would tell us we will do well on average on the real data distribution. So that's so I want to suggest that machine learning is sort of maybe one way to get around the fact that most of AI problems are computationally intractable in the worst case. Okay. So then, how would we go about trying to learn an efficient algorithm? So now I narrow down to something more specific, because then we do specific work, right? We'll look at inference algorithms in probabilistic graphical models. So one way might be to say, right, so we've been doing this for a long time, right? Let's restrict our models to something where inference is efficient. Tree models or some product networks, linear chain, and then we learn model parameters. So we are actually learning, in this case, an inference algorithm that's tailored for the data because we train it on the data to do well. So this is sort of one example. We've been doing this a long time. Or maybe we want to be right. This is restrictive, right? The model is restrictive. Chains, for example, or trees. Or maybe we don't want to restrict the models to chains or trees. But in that case, then maybe we need to use approximate inference algorithms. So I hope I have time. I'll go through one quick example of that, of our work on that. Right. So we don't restrict the model, but we stick to a known algorithm, and then we learn the model parameter. Again, we are learning from the data. Okay. Or the third case, we might become more ambitious and say, right, let's not restrict the models, and let's not restrict, not restrict the inference algorithms. Let's learn both. Right? Let's learn the models, and then let's learn the inference algorithm instead as well. Okay, so that we learn a better algorithm than a better approximate inference algorithm. Okay, so I'll talk about that first. Okay, I'm going to talk about, actually it's very much related to what Prof. Zhu just talked about, hypergraph or factor graphs. Okay, very quickly as a motivating example, let's see. Okay, as a motivating example, let's say I want to identify, I'm given sort of the mass spectrum of a molecule, and I want to identify the bonds in the molecule, right, between every two atoms, whether there's no bonds there, single bond, double bond, triple bond, and so on. So in this sort of problems, we have constraints that we might want to put in. Like it's known, for example, that atoms satisfy valency constraints. A carbon can only be connected to four other atoms, right? Out of 20 other atoms that's in the molecule, is restricted to 4. So we might want to put this sort of constraints. So graphical models provide sort of methods to do that. I'll talk about conditional random fields or Markov random fields. So in conditional random fields or Markov random fields, you are given right, you want to say what's the probability of the different configurations that are possible. And the way you say certain ones are more possible than others are you take subsets of variables and then you put functions over them. And you favor sort of configurations over the subsets that that you like, that they'll turn out to be more likely. So one way to specify this, you can look at this as a hypergraph or a factor graph. The way I'm going to present it is as a factor graph. Factor graph is a bipartite graph, a set of vertices. Okay, so set of variables, call it V, set of factors, call it C, and then it's bipartite. So between every factor and there are edges between factors and variables. Okay, so in this particular case, for example, I might want to say that these are between every two atoms, are there bonds or not? And then this factor might say that, for this particular set, only 2 out of 3 can take the value 1. So this might be that sort of valency constraints, or whatever sort of subsets that you might favor. Okay, so this is one way to specify graphical models. But I guess the thing I'm interested in is sort of the factor graph data structure, because we are going to do message passing over the factor graph data structure. Okay, so after learning, then usually in a graphical model, you're interested in doing something like this, right? Finding the configuration that maximizes, this particular value, right? The probability, let's say. Okay. So unfortunately, this is NP hard in general, and then normally we might end up using approximate message passing algorithm and various sort of approximate inference algorithms. One that I'll focus on is the max product, is the belief propagation algorithm. It works well on some problems, but then not so well on others. So I guess what we want to do is we want to say, okay, right, can we come up with a better algorithm, learn a better algorithm than the max product belief propagation algorithm? So, okay, right, so that's sort of the aim, right? So let's try to learn a better inference algorithm, right, from data, because we want to say do sort of average case algorithms, right? We want to solve well on the data that we actually see. So let's try to learn an approximate inference algorithm from data. I want to say I can improve on max product. How do I do that? One way would be to show, right, that my algorithm contains max product as a special case, right? So if max product can do well, then essentially we can imitate, because we are learning, right? We learn best on the training data. If max product does best on the training data, then we want to say we can imitate max product, so we'll do as well or better, right? So it's targeted towards the distribution of instances that we see. It's not a general purpose where we design for the worst case. Okay, and the way we'll do it, we try to make it differentiable with respect to all the parameters, so then we can do end-to-end learning with the target loss function. Okay, so that's sort of the aim. So very quickly, to let you see what the max product looks like. So the only thing I want you to see here is that it's a bunch of sums and max. That's all it is, right? And if it's a bunch of sum and max, then we can just parameterize neural network circuit, right? Or a neural network computational graph that can do this type of sums and max. And that's all that's all we need to do, right? And we make the network more powerful, right, than just this exact operations. It can do more operations. Then we learn the networks, it's parameterized, we learn it, and therefore we are able to learn something that contains this. It can simulate this as a special case, but it can potentially learn sort of more powerful operations. Okay? So that's sort of the case. And so this is one round of message passing for graphical models. Hopefully a lot of you are familiar with graphical models. Right? And it's sort of one iteration in this algorithm. We can construct it as one layer in the network. And if I want to do k iterations of this, I just construct k layers of this network. And I can simulate, for example, the max product algorithm. And hopefully, potentially more, right? Because I parameterize it with a richer class of parameters. So I can hopefully learn a richer class of algorithms. So that's sort of the idea. And okay, I think I'll go through this very quickly. This is sort of what one layer or one operation look like, one message passing operation looks like. Instead of fixing the sum and max, we just use a multi-layer perceptron. And then we just argue and do construction to show that we can simulate those sum and max operations that we are interested in. But potentially more, and it's parameterized, right? Then then you just put through stack multiple layers and then do gradient descent, and you can learn hopefully something more powerful than the algorithm you targeted in the first place. So that's sort of the argument. Okay, we ran some experiments. So this is the artificial data sets, just chain, but then we add a lot of high order potentials that are similar to the valence constraints, right? It limits the number that can take the value 1 to k. Right? We compare with the original max product with linear programming relaxation. Right? We learn it and it seemed on this artificial data set to work well. On real data set, this is a 3D point cloud semantic segmentation. It seemed to have done well. I think this is at least state-of-the-art result that we know of. So it seemed to do well there. Okay, so that's the vector graph neural network. So I want to very quickly try to run through another algorithm. Okay, another sort of idea. So okay, this time we are going to say let's fix a known approximate inference algorithm. In this case, we are going to use a particle filter, right, or sequential Monte Carlo, let's use more powerful models. Okay, so that's and sort of what more powerful model? What's been working very well in practice is recurrent neural networks. Okay, so we want to say what's very good about 10, 15 years ago, we always seem to think that these sort of things are very hard to learn. Latent variables are very hard to learn. But these days, we seem to just learn them. Practically, we seem to just be able to learn them. And our recurrent neural network, particularly the gated ones, seem to be able to learn. So we want to inherit the strength of recurrent neural networks. But recurrent neural networks, the latent variable, as you want to make it more powerful, you increase the size of the latent vector, right? And if you increase that, the number of parameters actually grows quadratically with the length of the latent variable. Whereas something like, the dynamic Bayesian network or graphical models, usually, right, they have a fixed number of parameters if you fix the model. And then if you use a particle filter, as you increase the number of particles, it doesn't increase the number of parameters. So we want to sort of combine both these advantages. Okay, so instead of using one RNN, we're going to maintain n weighted RNNs, right? And then we essentially do the particle filter updates. Okay, the transitions, and then we get the observations, and then we do resampling. And then we make the whole thing differentiable, and then we just run. Then we just do backpropagation to learn the parameters of the. So now essentially you can think of each particle as a LSDM cell or a GRU cell. Okay, these things seem to work well in practice in terms of being able to learn it. Okay, so so we can sort of transform an LSDM into a particle filter version of LSDM, GRU into a particle filter version of a GRU. We maintain K of them. Every step we do a transition, and then we do resampling. So resampling is quite good because resampling actually kills away the low probability hypothesis, right? And then allows you to sort of focus on the high probability ones, and then you grow from there. So that seems to be actually quite helpful. Okay, so again, experiments. So it seems to actually do quite well on that. We tried 10 data sets, and if you look at LSDM, right, this is over with hyperparameter search. The best LSDM we found was something like this, and the best PF LSDM outperforming in all, almost all 10 cases. GRU, again, in 9 out of 10 cases, it either matches or outperforms it. So that's sort of encouraging. Because it's encouraging, then we want to claim, right, it's a general purpose method that we can improve LSDM and GRU. Then we think, what are other general purpose methods? Ensembles, right? So we try to compare with ensembles. It outperforms it most of the time. This quadrant means that the PF version outperforms it, and this or regression, which use a different quad. This side showed it, so it does outperform ensembles. So we are quite happy with that. So let me finish off with a summary. So I guess the sort of idea I want to share is, right, if we want to develop algorithms, sort of learning targeted towards average case, right? One way is we can start with some algorithm we know of, sort of over-parameterize it so that it's more powerful, then we learn, right? And what do you get out of this? One is that we can show that, one algorithm can simulate another, therefore our vector graph neural network is more powerful, right, than the usual max product algorithm. And if we understand the original algorithm, like max product, we know it's exact on trees, on chains. It can do bipartite matching. Then if the learning works correctly, then the vector graph neural network also have these properties, right? And then we have generalization theory that allows us to connect finite sample training set performance with average case performance of algorithms. And my last slide. Okay, so again, I want to re-emphasize, right? We should probably target the actual data distributions because real problems maybe are not as hard as the worst case. So we have sort of a recipe, right? Take an existing algorithm, neuralize it. That seems simple, but actually it's a lot of hard work trying out many different things. When you do neural network, you know that, right? We want architectures that are easy to train, but that's not very well understood. We seem to be able to train some of them, not others, right? We don't want too many parameters because we want to learn with less data. But then, maybe we need more parameters to make training easier. So lots of issues. We want parallel computation, so maybe we want parallel algorithms. That'll be nice because we can exploit hardware. But then maybe in some cases serial computation is necessary. Not sure we understand that all that well. Okay, so what might be interesting classes of AI algorithms? The two classes that we tried, I think they work well on different type of problems. So one is a graph neural network, right? The other is a recurrent neural network type. I think that the algorithms only work around the neighborhood of those algorithms, whatever you call neighborhood, right? So we probably need many different classes of algorithms still, but hopefully we can improve them and target them towards real average case sort of performance, right? So the types that we usually use in AI might be message passing, sampling, heuristic search, continuous optimization. A lot of this we maybe can do these sort of things. And maybe it might be interesting to also try to extend it to adversarial environments. But even in that case, we actually want, because most of the space is either uninteresting or we are not interested or it's empty or whatever, right? Even when we want to do adversarial cases, maybe we still want to try to exploit data distribution. I think that's all I have. Yeah.
I didn't quite catch how the particles are generated. Is it in the Bayesian sense or in the...
It is a randomized algorithm. You end up with a randomized algorithm.
Randomized on what part? Data or?
No, input. So we do the reparameterization trick. If you are familiar with that, we use random data as input, and then because we use random data as input, every time we run it, it's actually a randomized prediction. But it actually works fairly well, even though we
mean by random data? You random.
Every time I get a new thing I want to classify or I want to do prediction, I give a predictor which takes in some random numbers, and it will make a randomized prediction. But I have k of them, right? So they probably are. It's not that unstable because I got k of them.
It's not drop off.
It's not.
It's not drop off.
No, it's not drop off. No, it's actually randomized. When you run it, it's actually randomized. It's a particle filter, right? When it's a particle filter, when you run it every time you might get a different answer.
What do you mean by randomized? Randomized meaning you resample the data, or?
No, every time I want to do a prediction, I get a random number and then I create a random prediction. But I have k copies of them, so it's not as random.
But you already have, but I assume you are training a network.
Yeah,
you make
so
a prediction before you have a network.
When we train, we do that. When we actually use it, we also use it. If you are familiar with like particle filters or sequential Monte Carlo, those are every time you want to use it, you do this estimation, right? You generate.
Just because I know those things so well, so I don't understand. I consider myself one of the inventor of the sequential but I don't understand what your framework is, because typical sequential Monte Carlo is it's in the Bayesian setting. You are estimating parameters.
But after you estimate it, then you use it, right? Okay, we are we are doing an estimation every time we get a problem. Right? Every time we get a problem, we do estimation. Yes.
Yeah. There are two states, that prediction update and measurement update, that
Right.
you use the density functions.
Yeah, we use a set of particles to approximate.
Yeah,
right?
you approximate, yeah, from this density function you draw the samples.
Yeah.
And normally in the state space representation, the models are given, so that
Right.
you can use.
Yes.
You can draw samples here.
Here we want to learn and we want to learn it, right? We want to take advantage of learning. Yeah.
Yeah, by this combining RNN, you aim to target property of X given Z, for example, latent given.
Okay, so the type of, we are essentially doing prediction. We are given a sequence of X and you want to predict Y, and you want to predict a sequence of Y. Right. And we have, I guess, latent states that we don't know, which we hope the RNN will help us learn. So we predict, given X, predict Y.
This density function is approximated by
learning, yeah.
by RNN.
By learning the RNN,
Yeah.
yeah. So it's all learned, we don't really know what it is.
And is the deficiency in particle filters, it is not scalable up to in higher dimensions, so it is
Yes.
much scalable.
Okay, so my contention is that a lot of AI problems are not that hard. Like you can track 30 hypotheses, you're very happy.
Yeah, if you compare
Right.
with usual extended Kalman filter kind of stuff, how is it? If you can apply.
We didn't try with comparing with extended. What we did was we took 10 data sets, we ran the original LSDM, GRU, and we ran this. So we didn't try with extended Kalman filter.
Okay, so let's say it's clear again, so to move on. Okay,